given a signal x of t, its autocovariance, which we denote by C with a subscript x, is by definition the autocorrelation of signal x minus its expected value. Since we are assuming ergodicity and consequently stationarity, we know that the autocorrelation will only depend on tau, which is the difference between t2 and t1. So the autocovariance can too be written as depending only on tau. Since the autocovariance is the autocorrelation of the signal minus its expected value, if the expected value of x is 0, then its autocovariance will be equal to its autocorrelation. And since the autocovariance is defined as this autocorrelation here, we can write it as follows. We will have a product of two things here inside the expected value. The first is x of t minus its expected value. The second is x of t plus tau minus its expected value. We can now develop this product, remembering that the expected value of a sum is the sum of the expected values, and that constants can get outside the expected value. In other words, that the expected value is a linear operator, and we will reach the following result. Now this is the autocorrelation of x by definition. This, of course, is the expected value of x. So all this will be the expected value of x squared. This too will be the expected value of x. It doesn't matter that the signal is shifted in time. So this, again, will be the expected value of x squared. We are left with the following result. The autocovariance of x is equal to the autocorrelation of x minus its expected value squared. Now, since the autocovariance is by definition an autocorrelation, we know that it will verify the following property. It never exceeds the value for tau equal to 0 and never gets below the symmetric of the value for tau equal to 0. The same consequently must happen for the autocovariance. It can never exceed the value of the autocovariance for 0 or get below the symmetric of this value. And we know that the autocovariance for 0 must be given by this expression too. So here we will have the autocorrelation for 0 minus the expected value of x squared. But you remember that we saw that the value of the autocorrelation for 0 was equal to the expected value of x squared plus its variance. Consequently, we see that the autocovariance for 0 is equal to the variance of x. So the autocovariance of x never gets above its value for tau equal to 0, which is the variance of x, and never gets below minus the variance of x.